Hey everyone, I am going to introduce to you the electrical potential energy of a system of charges. And the best way to approach this installment is just by an example, because an example will show you how to calculate the electric potential energy, the total, that is, electric potential energy of a system of charges. I am super excited to introduce you to this kind of like knowledge because it's really amazing. Okay, so let's assume in this example we have three charges. Okay, so charge here and charge here and charge here. So we have three charges. The triangle is actually a virtual triangle, it does not exist, but we just want to identify that these three charges sit on equilateral triangle and the side of each is 0.75 meters. So this charge here is 3 nanocoulomb and this charge here is 2 nanocoulomb and this one here is minus 4 nanocoulomb. So we have three charges. We know all the charges and we know all the distances between the charges. The question is, find the electric potential energy required to keep the system of charges within the vicinity of each other and they hold this uniform kind of like distribution, if you will. Okay, so how do we do that? There's two ways. The first way is using the physics way, and that's how we learned about it. And the second way, once we actually learned how to do it in the physics way, there is a shortcut that we can take. And this shortcut is purely mathematical. So let's just do the physics first, the physics one first, and we will do it only once because it is really important to learn the physics concept behind it. Then once we understand it, then all other problems will be solved just using the mathematical tool we will learn later. Okay? So, how do we go about doing this one? First of all, let's actually call this charge number 1, and let's call this charge number 2, and let's call this charge number 3. So we imagine that this whole system does not exist. So this whole system, first of all, to start the physics way, we imagine this whole system does not exist. Okay? So let's imagine it does not exist. So if you want to mask it, you can, or whatever. But let's think about it this way. So I'm going to actually put it away, all right, for now. And let's start with this charge. So I'm going to go to the infinity all the way away and bring charge number 1 from infinity and set it here. And this is 3 nanocoulomb, all right? Now this charge, to go to infinity and bring it in, will require actually no work, because it was an infinity and I brought it somewhere that is similar to infinity electrical wise. There's nothing around, still like it's not feeling any forces or any energy from any other charges. So we're going to assume, and it's a correct assumption, that bringing it from infinity all the way to here will require no work or no energy. So I'm going to call this W1 and I'm going to call this 0. Now, I am going to go to infinity again and bring in charge number 2, which is this one. Okay? And charge number 2, I'm going to go and bring it here, and this is 2 nanocoulomb. Now, this would require energy, because as I'm bringing this from infinity, it will feel the presence of this charge. So basically, you have to find the work required to bring this charge from infinity to the presence of the first charge. And I'm going to call this W2. And W2 is equal to K Q1 times Q2 divided by the distance between them. Okay? And if we plug in the numbers here, so I'm going to say that's 9 times 10 to the power 9. Q1 is 3 nanocoulomb, so I'm going to say 3 times 10 to minus 9 times this one, which is the other charge that we brought from infinity, 2 nanocoulomb, 10 to minus 9 coulomb, and divide by the distance between them. That's 0.75. And if we do this calculation correctly, we will get an answer equal to, for W2, is equal to 7.2 times 10 to minus 8 joules. So that's how much energy we need to bring charge number 2 from infinity within the vicinity of charge number 1. Now, we go all the way to infinity to bring in charge number 3. So I'm going to go here, since this is already a drawn triangle. So I'm going to go here to infinity all the way and bring charge number 3. Okay. Now, as I do that, charge number 3 will feel the energy or the presence of charge number 1 and charge number 2. So to find the work for it, so I'm going to say work for charge number 3 should be equal to K, first of all, that's the equation, Q3, right, times Q2 divided by the distance between them, which is the same, R, plus K Q3 with the presence of this charge Q1 divided by the distance between them, which happens to be the same distance. Okay, now just to make things easier for our calculations, we can take K and the common term here, K and Q3 outside, and we are left off with Q2, and we can take R actually outside too. We are left off with Q2 plus Q1. So that's nice. That makes it easier. So K is 9 times 10 to the power 9, and Q3 is minus 4 times 10 to minus 9. Notice that we put the sign of the charge Q3 because it's minus. We put it here because work is energy, and energy is a scalar, so we plug in its value, whether it's positive or negative. We plug the sign with it too. If it is negative, we put it negative. So now this is divided by, now the distance here is the same as the distance here, which is 0.75. We agreed on that. And Q2 plus Q3, Q2 plus Q1 is 2 plus 3, which is 5 nanocoulomb, 10 to minus 9. So that was good. All right. So now, if we calculate this whole thing together, we are going to find that the whole W2 is equal to, or W3, I'm going to put it here. So W3 is equal to minus 2.4 times 10 to minus 7 joule. Right? Good. Now we found W1 and W2 here and W3 to find the total energy required to keep the system of charges like this. Basically, we just add them all. So I'm going to call this W is equal to W1 plus W2 plus W3, and W1 is 0, W2 is 7.2 times 10 to minus 8 plus W3, which is minus 2.4 times 10 to minus 7. And once we add all of this, we get the total electric potential energy, or the work, is equal to minus 1.68 times 10 to minus 7 joules. So that's the answer for this problem. Okay? All right? Now we are going to use what we learned from this problem and solve it more quickly in a shortcut and nice mathematical way, and I'll show you how to do this. Okay? So, to learn the mathematical way, it's a good idea to look on our terms. Okay? So let's look at this term first, which is W2. It's equal to Q1 Q2 over R. Okay? Now W3 has two terms in it. K Q3 Q2 over R plus K Q3 Q1 over R. And the first one is 0, so it doesn't count. So let's write these together, because this is actually what contributes to this, right? This is all. So let's write them all together. So W, the whole W is equal to K Q1 Q2 divided by R plus, now let's go to this term, K Q3 Q1 divided by R plus this term, final one, K Q3 Q1, this one here is Q2, this one here is Q2, okay? And now we go back to the third one, the last one, 3. So if you look at those all, so you have Q1 with Q2, Q2 with Q3, and Q1 with Q3. So these are in math called permutations, okay? And each one has K, 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 R, 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 which is the distance between Q1 and Q2 here happens to be R, the same distance as the distance between Q3 and Q2, and the same distance between Q3 and Q1. But these things are called permutation. What is that? So we said Q1 with Q2, Q1 with Q3, then Q1 with Q2, then what's left is with Q2, Q3, and these, all the terms are here. So basically you want to include all the terms, the permutation of all the terms, and that's how you get the answer very quickly. And if you do this, you will find W is equal to minus 1.68 times 10 to minus 7 joules. And that's it for this one. See, you can solve it so easily in almost one step if you know the permutations. And the permutations is just like you make all the permutations you have. Q1 with Q3, Q1 with Q2, and the last one, Q2 with Q3. And there it is. And that's it. It's exciting, isn't it? All right. Let's go to the second one, and that one will be a little bit more complicated. Okay, so let's check out this example together. We have here a square, that's just a virtual square to show us where we should put our charges. And we need to calculate the electric potential energy to keep this system of charges together. So we have here, we have one charge, and we have one charge here, we have one charge, and we have another charge here. This charge is 3 picocoulomb. This charge is minus 6 picocoulomb. This charge is 7 picocoulomb. And this last one is minus 2 picocoulomb. Pico is 10 to minus 12 as an index. All right, so now we have this distance is 1 meter, and this distance here is 2 meters. And we need to find the electric potential energy needed to keep this system together. Okay, great. Now, as I said, we can solve this problem by bringing each charge from infinity and fields within the vicinity of other charges, and that for this system of 4 charges is going to take a long time to solve. But we can actually learn how to do it in another way. We can call this charge number 1, this is charge number 2, this is charge number 3, and this is charge number 4. And we can do it using permutation as in math, okay? So basically, charge number 1 with charge number 2, that's one term in this process. Charge number 1 is with charge number 3, that's another term. Charge number 1 with charge number 4, that's another term. And we do the next 4 permutations. But before that, let's write down the general equation. The electric potential energy, which is known as W, work, is equal to K, one charge, times the other charge divided by the distance between them. Let's call this charge number 1, that's charge number 2, just to distinguish between the two. Okay? So what permutations do we have? So I'm gonna do the total work, okay? Is equal to K. Let's take charge number 1. I'm gonna say Q1 times Q2 divided by the distance between them. I'm gonna call this distance R2. I'm going to call this distance R1 just to distinguish between the two distances. That's R2 plus, now charge number 1 and charge number 3, K Q1 Q3 divided by the distance between them. Okay, so that's another distance. I'm going to call it R3 plus charge number 1 and charge number 4, K Q1 Q4 divided by this distance here, which is R1. All right. Now we're done with charge number 1. Let's go to charge number 2. So plus K Q2. Now we can't take Q2 with Q1 because that's already here. Q1 and Q2 already have been counted for in the permutation. But we can take Q2 with Q3, divide by the distance between them, which is R1, plus Q2 with Q4, K Q2 Q4 divided by the distance between them, which is the same as R3. Okay, is that it? Yes, because we already included Q2 with Q1. All right. Now let's take this charge, Q3 plus K Q3. We cannot take Q3 with Q2 because this term already exists, Q3 with Q2. We cannot take Q3 with Q1 because this term already exists. So we only have a choice with Q3 and Q4 divided by the distance between them, and that we called R2. Now, is there any other permutation? The only one left is Q4. Did we take Q4 with Q3? Q4 with Q3 is here. Did we take Q4 with Q2? And that is here. Q4 with Q1. There it is. So all the Q4 permutations are accounted for. So this is it. We just have to now simplify as much as we can, then we can solve it. So W total, I can take K outside, and let's see the Q1 and Q2, Q1 and Q3, Q1 and Q4, all in the picos. So all of them are multiplied by 10 to minus 12. So we can take that outside too, so that to simplify things, okay? So 10 to minus 12 here, 10 to minus 12 here, so 10 to minus 24 as a total. We cannot take R outside because it's different each time, so let's just keep that inside. So that's K, which is, this K is 9 times 10 to the power 9, okay? So we end up here, Q1 is 3 times Q2 is minus 6 times minus 6, and divided by the distance between them is what? 2, plus Q1 is again 3 multiplied by 7 divided by R3. Now R3 is what? I'm going to calculate it here. R3 is equal to root square of 2 square, which is 4, plus 1 square, which is 1, and that gives us root square of 5. And that's it. Divide by root square of 5. Plus Q1, which is again 3 times minus 2 for Q4. Divided by the distance between them, and that's 1. Right? Now this term, plus K is outside, minus 12 is outside, as we mentioned. Q2, which is minus 6, multiplied by Q3, which is 7, divided by the distance between them, and that's what? 1. Plus Q2 and Q4, and that's minus 6 times minus 2, divided by the distance between them, it's root square of 5, plus the minus term, the last term, which is K is outside, Q3, that's 7 times Q4, which is this, minus 2, divide by the distance between them, and that's 2. Okay? And doing the calculations, that gives us 9 times 10 to minus 15, okay, times all of this inside, and I calculated that to be minus 49.23. And do this calculation together, you get total work required to keep this system of charges within the vicinity of each other in this shape is equal to minus 4.43 times 10 to minus 13 joule. And that's it. I hope you liked this example. Thank you.